don't open your mouth and all of a sudden I carry that mistake for like 25 more minutes. Like, oh man, come on, correct me. All right. Okay, so the purpose of today is to understand how we use net potentials as a way to predict whether redox reactions occur and to actually quantitatively get the voltage of a battery and what it means. What does voltage really mean and how does it tie into spontaneity? So there's a lot of concepts here that I know people have holes in their understanding because I think they have holes in working with redox reactions. I bet if I go look, and I don't have the time, but I will at some point, a lot of people struggling here haven't gone through the Module 10 this summer assignment, or you forgot it, who knows? But let's get started. So here's what I have, okay? I've got good old-fashioned copper, as opposed to modern copper, I'm not sure. But in any case, there's copper, and here is tin chloride. It's a solution. Now, because I write aqueous, that really means I have what? Tin plus 2 and chloride ions flying around. We write tin chloride. Now, over here, I've got tin. Nice, pretty piece of tin. And the solution over here, and let me just write it where I can. Oh, the tin's going to get in the way. Well, the solution here is copper chloride. And it's aqueous, which means I have copper plus 2 and chloride ions flying around in solution. Why? Because the water can dissolve them. Why? They're soluble. Why? The charges between them are weak coulomically, things we've covered. Okay, so these are two solutions. Now, you'll notice that this guy isn't as soluble. That's why it's a little bit cloudy. There's some precipitates, but some of it dissolves. Okay, so here's what we're going to do. I'm going to put the copper in the tin chloride. Okay? Boom. All right, and we'll start with that one. And we want to see what could happen here. We're going to see, will this react? Will there be a redox reaction? Now, let's look at the players here, okay? Now, here is what we call the reactants. I've got my tin chloride aqueous, and I can write that in for all intents and purposes, okay? And let's go blue, feeling blue today. Aqueous, to remind myself, that's ions floating around. Does everyone know what the phase of a metal is when it is not bonded to anything? Is it a solid, liquid, or a gas? Anytime you've got a metal that's an elemental state, which means it doesn't have a charge. Protons equal electrons. I say atom, you say neutral. This is zero charged, okay? And anytime you've got a metal, and you say, well, Mr. Grotsky, how do I know I have a metal? Metals are below this staircase here, so copper's over here. These guys are the smalls, these guys are the bigs, okay? They tend to lose electrons, right? Okay, so copper 0 is a metal, and it's a solid phase. All metals that have charge of 0, elemental states, are solids with the exception of mercury. It's a liquid. Okay, now what are we trying to do here? Does this reaction, and what would it make? Okay, well I'm going to help you with this. It's called a single replacement reaction. Let's do the individual oxidation states. Your first skill in redox is to write individual charges for elements in a compound. If they're hanging out by themselves, 0, easy. But these are two different capitals, two different elements, so they have different charges. The one in front is always positive. So when I go to the periodic table, I will find that tin can be plus 2 or plus 4. I'll give you that at some points. Chloride, check it out. It likes to become negative. It's a small, it gains. And how many does it gain? It always gains how many it takes to become stable, like the noble gases. That's from the summer. We'll talk more about that. But it likes to become -1. All of the halogens individually love to be -1. Look at F. If we're F'ing around, F becomes -1. Cl likes to become -1. Bromide -1. Can we guess what charge oxygen likes to become? -2. Right. Okay. These guys like to lose 1 and become +1. These guys lose 2, become +2. Oh my gosh. Okay. So this doesn't mean Cl bonds with itself in -1. Don't do that. That just means you've got 2 of these chloride ions individually. So the overall charge due to both chlorines is -2. Hey, there's only one tin. The whole thing has to equal 0. Why? Because there are no charges written. So they have to equal 0. So the overall charge for tin is +2. And because there's only one tin, It's individually plus 2. Now, let me try to explain what we think could happen here. Chlorine already is -1, correct? From things we've already learned, if chlorine becomes -1, it already has the electron it wanted to attract to become stable. So it's kind of not going to do nothing. It's not going to do anything, I should say. It's going to spectate. Ooh, tin plus 2 is plus 2. Couldn't it attract the electrons on the outermost of copper? If this could react, party people, this is the possibility that the outermost electrons of copper could be pulled away to the tin. If this is going to react, copper is going to oxidize, Leo, lose the electrons to tin. And this is important today. In order to have a transfer of electrons and be a redox reaction, 2 things have to occur, or one of 2 things. Tin has to be strong enough to either yank these electrons, which we call what kind of agent? Oxidizing. Or copper has to be weak enough or strong enough to push them away and be a reducing agent. Itself gets oxidized. Think opposite. The best analogy, so we think of the one oxidizing, how hard does it push? And the one getting reduced, how hard does it pull? My friends, in chemistry, how much it does that is measured in its individual volts on that table. We'll get there. So the best analogy is a guy named Kevin. Hey, Kevin. I don't know why Kevin, but I'm sleeping with him. He's got a man purse. Okay, I'm not sure. Okay, and there was another guy named Todd, and he liked that man purse. Went with his outfit better, so he's not a very good character, not good very standing. Okay, so he went to take Kevin's man purse. The question is twofold. How strong is Todd? If he's buff and really strong, he probably could pull that man purse away from most people, correct? He'd be like a strong what? Oxidizing agent. But does that mean if Todd, who wants the man purse, is big and buff and strong, is he going to pull man purses from everybody? No, there might be someone like Kevin who might be big and strong and stronger than he is to hold on to it. To consider if a redox reaction occurs, we have to consider the strength of both. If Kevin, who has the purse, is really weak, and this guy's really strong, you're going to have an aggressive transfer of the man purse. Okay? So we have to evaluate the individual abilities. That's what the voltages do for us. Okay, we'll get back to that. Now, we don't know if this occurs, okay? But we do know what could happen. So let's write what could happen. If copper was to react, it's going to lose 2 electrons. What's its charge now? If it loses 2 negatives.
Yeah.
Hey, I'm neutral. Are you sad, Mr. Grotsky? No. Are you happy? No, I'm neutral.
Yeah.
But if I lose my negativity? Right. Okay. So copper. See, I couldn't do that demo with the mask. Sorry. Okay. Or I need a see-through or something. Sorry. Maybe I should get a shield with some, like, I don't know. Okay. I'll work on it. Copper plus 2. Hey, what's chlorine doing? Nothing. It's going to hang out. It's going to spectate. Let's write a chemical formula. You did this summer. This is a salt. It's making a crystal. Positive, negative ions. Don't I need 2 of these for every one of these in the crystal? So it'd be like this. And therefore, the whole negative side is -2. This is plus 2. That's our compound. Hey, who's going to kick out? Yeah, tin is hooking up with the chloride ions, theoretically, because it's positive. But once it gains electrons, it has no charge. It's not going to attract the Cl negative, so it's going to be just tin hanging out. And this is our reaction. And by the way, what phase is tin? By the way, it's tin because it's stannum. Stannum is the Latin name for tin, by the way. Okay. In any case, so that's going to go solid, right? And this would be aqueous. So this is our proposed single replacement. It makes sense. He's going to get positive because he gains electrons, if it does work. Let's write the proposed half reactions. And this is where some people have some some weaknesses. I'm going to pull out the two processes. There's one process where I'm losing electrons. I know this is theoretical, so I don't know if it works yet. And someone's gaining them. Let's do the one losing, Leo. That's oxidation or reduction. Right, so let's write out copper. Copper is on the left-hand side, so I write it out as copper 0. Okay, what does it become in the future? Copper plus 2, so I write it there. Okay, let's do it for the other guy. Tin is on the left-hand side, the right-hand side is plus 2. And on the product side, 0. Nowhere, no how, do I have chloride ions in here. They're not losing, they're not gaining. They're both individually -1. There's a question. Neither oxidized nor reduced. It spectates. Okay, so I'm not going to put it in here. In chemical reactions in AP chemistry, we always write net ion. We don't ever do things that don't do anything. We'll do more of that. Now, we're not done here. A half reaction, if properly written, must have the same charge on both sides. Why? Because we have to have the law of conservation of charge in play. So how do I go from 0 to plus 2? We know it's a difference of 2 negatives. But do I put the negatives on this side or that side? Well, the charge is going up. I'm getting happy because I'm losing my negatives. Products are produced here. So I write electrons as an E negative. Each one's negative. I put a 2 in front. That doesn't mean I gain 2 electrons. This means that I make 2 electrons and a copper. That's what that means. And by the way, look at the charges. 0. What's a -2 and a +2? 0 on both sides. Now, if you ever write a half reaction, or half reactions for a redox reaction, and you got electrons on both sides, you know you did something wrong. Someone's going to produce them, someone needs to absorb them. Okay? How did I go from +2 to 0? Didn't this charge go down? Got reduced. This charge got reduced because it gained negatives. And you gain something, it's in the reactant side, like energy in an endothermic reaction. And notice something, party people. The same electrons that were produced are the same electrons absorbed. That's what this is showing. I'm really showing that by writing this. And a couple of keys here. This came out nice and easy. What if this was 6 electrons? If I produce 6 electrons, don't I have to absorb 6 electrons? I'd have to distribute a 3 here. 3 times 2 is 6. Okay, to balance. We'll get to that another day. Okay? But in order to have it properly written half reactions, electrons have to cancel. This is called law of conservation of charge. Why? The same number of electrons that are lost better be the same electrons that are gained. Because if it's not, then you're saying electrons are produced or they're lost in the process. They're not. Electrons are just, hey, exchanged in nature. We don't make them. Okay? Now, here's what I'm going to do. And I didn't write it in here, but I think it's important that I should. I'm going to write the overall net ion reaction. When I say net ion reaction, I'm taking away the players that are spectating. If you're going to watch a sporting event, you're spectating. You're not involved. Chloride negative did not get oxidized nor reduced. So watch what I do here. I'm going to put this half reaction together. I always know that I'm done when I cancel my electrons. The same electrons that are produced are the same electrons that got absorbed. These are the electrons being passed around. They have to be the same number. And then I write all my what? Reactants. Copper 0 plus Sn plus 2 goes to Sn0 plus copper plus 2. That is called the net ion reaction. And another way I can do a check to make sure I did it right, what's the overall charge on the reactant side? What's +2 and a 0? 2. Good, so it's +2 on this side. What's the overall charge on this side? 0 and a +2. +2. I know I did it right. Okay, now, who got oxidized? Who got reduced? Who gained electrons specifically? If you say tin, you're wrong. Tin plus 2 gain electrons. You better say it right. Who specifically in our proposed reaction must have gained electrons from the copper? Tin plus 2, not tin. If you say tin, you are talking about tin metal, which, by the way, you never pick anybody in the product side. This is the result of reactions. I always say this way. We're in a West Hampton Beach party. They're usually not good. The police go after the buyers and the sellers. And it's the sellers and the buyers. Right? Okay, say amen. Who actually lost? Who actually gained? The answers are always on this side. So party people, okay, who got reduced? Who specifically gained 2 electrons? Tin plus 2 did. Who specifically lost electrons? Copper. You can say copper 0. Now, if you meant to say copper plus 2, you got to say that. That'd be wrong. The players are on the reactant side. Easy stuff here, hopefully. Now, who got oxidized? I'm sorry. Sorry. That's not right. Copper is here. Who's the oxidizing agent? Think opposite. I'm the one who got reduced. So it's tin plus 2. And by the way, the wording is also catchy. If I say oxidizer, I'm talking about the oxidizing agent as well. Who's the reducer? It's a reducing agent. And the reducing agent is the one that gets oxidized, for reasons we have explained. Okay, the question is, hey, we did all of this, identified what things are if this reaction works. Does it work? I don't know. We're going to find out in front of us and by using their potentials. But before we do that, we're going to take a quick commercial break. No, we're going to go on to the next reaction. Okay? So, I'm going to take tin and put it in copper chloride. I'm going to go a little faster now. Okay, let that sit there. The best that it can. All right? And we're going to go a little faster now. Tin is what charge? It's a standalone metal.
0.
Okay, chlorine's -1. What's the charge of copper in copper 2 chloride? +2. Okay, so if this works, it must be, okay, electrons from the tin are trying to push its electrons. Or copper +2 is strong enough to pull the man purse. It's a combination. Now, if that happens, tin is going to become +2. If it loses electrons, it becomes positive. Chlorine, like I just told you, standalone. -1. Hey, if this is -1, this is +2. How many chlorines do I need? 2. There's the chemical formula. I'll leave the charges there just to notice something. Hey, if copper gains 2 electrons, doesn't it become copper 0? Why would it attract to negative chlorine? It wouldn't. It'd be popped out. And so what am I saying here, party people? In this reaction, if it works, we produce copper. In the other one, if it worked, we produce tin. Okay? So, real quickly, let's do the half reactions. SN0 is going to go to SN plus 2. In order for it to do that, it must lose negatives. So I put how many electrons on the product side? Right, so that both sides of the half reaction have the same charge. The next player, if this works, copper plus 2, is going to gain 2 electrons, and it's going to go to copper 0. Right, the net ion reaction, you can't see electrons. I gave you another easy one, where you had to do what? Just cancel out the electrons. If this was a different number, I must use the distributive property. Right now it's easy. Write the net ion reaction. Take out the spectator ions. It would be what? Copper plus 2 plus tin 0 goes to copper 0 plus tin plus 2. That's the net ion. All I did was add up all the stuff on this side. Electrons are never involved in the net ion. Never. Because they're canceled. Net means what? You guys work. Who works? You guys, you have money taken out? You have gross pay, the actual money you made. Then net is after you pay your taxes and Social Security. I know most of you guys can get some of that back. Okay? So this is the net after, hey, I give you $2, you take away $2. The net is you didn't get any extra money. Okay? All right. So who got reduced? Who is gaining electrons specifically? Copper positive 2. Copper would be wrong. Copper plus 2. And of course, it's the oxidizing agent for reasons we've explained. Who specifically got oxidized? Tin. And of course, it's also the what? Reducing agent. Question is, do these work? Same question is there passing electrons? Same question is it spontaneous? Same question is there a pathway allowable by nature that was allowing electrons to go from the guy holding on to the man purse to the one who wants it? Is there a good combination that provides a pathway? And if so, the reaction works. It's spontaneous. When I burned this piece of paper this morning, it's spontaneous. It works. If it's not spontaneous, there's not a pathway, it means that the guy holding onto the man purse is too strong, or the one who wants it's too weak to grab it. It's a combination of both. That's why we call them net potentials. So we're going to have to go somewhere to look at the strength of the guy holding onto the man purse or the guy who wants it. And that's what the standard reduction potential tables give us. That's where we're going now. Okay, so now it's important you understand what this is. This is standard. This means this is done at a certain set of conditions. It's not so important today, but here's what this is. What is a potential? A potential difference is a voltage. What's a voltage? It's the energy to push the charge or pull the charge. Okay? So, there was something called a standard experiment. And in this experiment, they measured how well individual chemical species or elements were able to push or pull. I'm going to explain that at a later date. We don't need that for today. But let's check this out. What is reduction? Gaining electrons. Electrons in the reactant side. We just did 2 of them. Always, always, always is reduction where electrons are with the reactants. These guys are gaining negatives and they go down. F becomes F negative. Same thing. So these are all written. Every single one's written as reduction. Okay. Now, what is voltage? This tells me how strong I am to do what? Pull 2 electrons from somewhere. Look at fluorine. It's got the highest reduction potential. It has the highest strength to do what? Pull electrons from things. If I breathe fluorine gas, I die. The fluorine gas will take electrons directly from the glucose and now never let it get to the what? Electron transport chain. It'll pull electrons everywhere. Okay, it's too aggressive. We can't survive in fluorine. It's deadly. Oxygen, not quite as strong, but still pretty strong. That's a good balance for us. Now, what's happening as I go down? What's happening to the strength? It's decreasing. The ability. Who was the guy that wanted it? Todd. The ability of Todd, okay, and I have a friend named Todd, so he's going to hate me using this. The ability of Todd to pull the man purse away is doing what? Decreasing. And as we look, these guys are so bad, these guys have negative voltages, which are telling you negative volts mean you have to add that energy back in to make it happen. These guys are so bad at pulling electrons, you got to force them. Think of a guy named Todd. Go get the man purse. I don't want to. I don't want to get the purse. You better get that purse. Okay. You gotta give him energy. Okay? So these guys don't want the man purse. You gotta force them. That's not spontaneous. Spontaneous is when you're paddling with the current. You don't gotta paddle anymore. You're riding a wave. The wave is taking you. The wind is blowing the turbine. We don't have a wind blowing the wind that blows the wind that blows the wind. Batteries! Batteries are spontaneous. You don't have a battery working a battery to work a battery. Batteries by themselves give off energy. Okay? Things that burn go until you run out of stuff. So party people, these guys are so bad. And going in the direction of grabbing the purse, it must mean what? These guys are really good at what? Pushing the purse off. Here, take it. So think about it, and this is the best way to think about it. I know I may have done it, I'll do it again. This is cellulose made of carbon. It loves to react with oxygen. Oxygen is strong enough to yank the purse away, electrons, away from the glucose. The carbon becomes positive. It hooks up with the negative oxygen to make CO2 and it flies away. Is this spontaneous? Yes, I used to start. Is it going by itself?
Yes.
Yeah, it's going to keep going until what? I put it out. Do I need this on the entire time? Once I take it away, it stops? What's the best example of non-spontaneous process? When you take the energy away, it stops. For those who don't see me, I'm taking the light away from my growing plants. Even though there's the photosynthesis on. Photosynthesis off. Photosynthesis is non-spontaneous. If there's no sunlight, there's no photosynthesis. If there's no wave, there's no what? Surfing. Okay? So party people, there's a pathway. Now, how do I know that this is really spontaneous? Well, I saw it happen, number one. But two, think with me. Think with me. There's a pathway in nature for carbon atoms to become CO2. It just happened. It happened real easy. That told me, number one. Here's the best way. It's combustion, burning of carbon sources, is so spontaneous. It's so good in going in that pathway that it's terrible going in the what? Have we ever seen paper reappear? Dude, it's precipitating paper today. Dude, it doesn't happen. We're never going to see the CO2 come back with the water to produce the paper. That doesn't occur. Well, guess what? Lithium is so strong at pushing electrons, the reverse reaction can't occur. You can't do both in nature. Nature gives you a pathway. And if you're really good at it, the reverse is impossible. So, party people, what is this telling me? Well, reductions are pretty good. Okay? Hey, I'm really good at reducing, which is what? Pulling electrons. F negative is what? What's the charge of F? What's the value of F negative to oxidize? Negative 2.87. Who's the most reactive metal? Who is the strongest reducing agent, or who is the best in this group? Because what would be its oxidation potential? Going this way, I got to flip the charge. Positive 305. Okay? Now, check it out. Let's look at gold. Gold is AU. AU, guys. Okay, so let's go at gold. What does this tell us? 1.50. That AU plus 3 likes to gain 3 electrons to produce gold. That is spontaneous. We don't need any energy. AU plus 3 loves to gain 3 electrons. Which means what? Gold is terrible at what? What's its oxidation potential? Negative. Gold doesn't lose electrons to become gold plus 3. It doesn't rust. Gold is not reactive unless you force it to happen. Okay? Now, let's check this out for a second. To see if a reaction works, we have to look at combinations, right? Okay, now watch with me. Is fluorine good at pulling the electrons or the man-purse away? What's its strength to be an oxidizing agent or good at reducing? 2.87. That's its value. If I hook it up with gold, okay? Gold hates to oxidize, so what's its value? Negative 1.5. Anytime I do oxidation, I have to flip the sign. This guy's so good going this way, it's terrible going that way, correct? So what's the net paycheck? 2.87 positive plus a negative. I can see that the positive is bigger than negative, so I know its overall net, after they take the taxes out, going to be a positive value. What does that tell me? Will that redox reaction occur? Yes. F2 is so buff in doing what? Pushing the purse. That even though gold doesn't, I don't want that, you can push it onto him and force it to happen because it's overwhelmingly can overcome the negative that gold is. You with me? Good. Now check out this. Gold was discovered in antiquity, before history, written history. We think. People discovered it because they saw it glimmering in a river. Okay? Gold's been around, and by the way, it melts at low temperatures, so you can shape it to almost anything you want. Why is gold shiny forever? Because we don't have fluorine gas. We don't have this really in nature. We have this in nature. Oh, oxygen, its strength to get reduced or pull electrons from things is 1.23 positive. What's the charge of gold oxidizing? Negative 1.5. You add them together, who's going to be? Gold is more negative in its oxidation than oxygen is positive in reducing. What does that mean? Gold holds on to the man purse stronger, then oxygen can yank it, and there is no flow of electrons, and oxygen doesn't reduce. People looking at their times. Am I past the time or something?
No.
Am I past the period yet?
No, you have 5 minutes.
Okay, for the first period still?
Yes.
Okay, good, thank you. I need the help. All right, because I can do this all day. All right, now, so you're with me, right? That's kind of cool. We're going to do this right here. Okay, so what was the first reaction? The first reaction, we had copper 0, okay, and we had tin chloride, okay, going to tin, and then copper chloride. So, question is, what is the strength of the copper to oxidize? Let's go. So I go to this sheet. By the way, I didn't give you a hard copy today because it didn't print, but you have one. So you're going to need this for your other parts. So let's go find copper. Okay? And I'm a loser. I know these values already, only because I just did last period. But okay, so for copper to oxidize into copper plus 2, that's going opposite of this chart. I've got to flip the sign. What is its oxidation potential?
Negative.
Ah, correct. Negative 0.3 volt. We say volt in Riverhead, I don't know why. Okay? Now, tin is plus 2, it's going to go to 0. Yes?
So hydrogen, 2 hydrogen. Does that is it like?
Okay,
does
the
it
reason
go-
why that is 0 is we use this to compare all others with. Okay, and I'm going to explain that another day. But it's a good point right there. So hydrogen does do stuff. Okay, and this is what we compared to. To get these values, we had to compare it to something. So we compared it to this standard cell. And what that means is all of these are that much better at reducing than H plus 2. And all of these are better in oxidizing than H2. Okay? So that's a great question. We put both of these in a cell and we saw which way it forced the reaction by how much. Really great question. Okay? We'll get to that. I didn't want to throw that in today. Okay, but that helped you. Awesome, awesome question. Okay, so yeah, so that's what's there. It's compared to both of these values. Okay, so any case, where was I? Okay, so back to the reaction. We had what? We had tin plus 2 becoming tin 0. It's getting reduced. So tin plus 2 getting reduced. I'm sorry, tin plus 2 is getting reduced. Yeah, so we're going this way. And that's what? Reduction is as written. This is a reduction chart. So you take the values always as is for reduction. It's the oxidation you have to flip the sign. Okay, so when you go back to the chart, let's go back to where we were. Okay, let's go back to standard reduction right here. Let's put it in. So for tin getting reduced, it's negative 0.14. These are the individual ones. And it's volts. That's the strength. It doesn't like to do it. It doesn't like to do it. The negative means you've got to force it to do what?
Or take it.
All right. In this case, I'm sorry, this is tin oxidizing, right? What do I have here? I have
Tin reducing.
Yeah, I need the top. I'm sorry, top one. Okay, so tin reducing is negative 0.14. Sorry, I thought it was on the top. That means tin doesn't what? Doesn't like to gain the man purse. I don't like that. Not really. Ew, whatever. How about copper oxidizing? That means I'm going the other way. I had to flip the sign, right? So that was what? Negative 0.34. Because this is a net, E0 cell is electromotor force. It's also called a net potential. You add them together. They're both abilities. What you get is negative 0.48 volts. Overall, when you consider the ability to oxidize and reduce, you get a total negative. What does that mean? It's non-spontaneous. What that means is, for this reaction to work, we have to keep forcing it, like photosynthesis. Got to keep putting energy in. We've got a motorboat going against the what? Current. Stop the motorboat, it stops. Okay, or goes backwards. And therefore, non-spontaneous. There is no pathway for electrons to be passed around. So there is no reaction. And here it is. There's no, so we didn't make what? We didn't make any tin. And here it is, just sat there doing nothing. Now it may look a little white to you. It'll be all white. But it's because of the precipitates. It didn't do anything. There's nothing there. Sat there, no reaction. Okay? By the way, electrolytic cells, batteries die. You have to recharge them. You have to put energy back in. Why? It may go spontaneous, and then you have to do what? Force reactions that don't occur naturally to occur. You can make this happen. Let's look at the other way. Okay? Now, you can do this fast, or we can do this, make sure you understand. So check this out. We have tin doing what? Oxidizing. So tin oxidizing. Let's go. So we go tin oxidizing. Tin 0 becoming tin plus 2. This is the reaction. I'm going this way. What do I do with this charge? Flip it. Becomes positive 1, 4. What's the other one? Copper plus 2 is reducing, right? Copper plus 2 is getting reduced. This one is positive 0.14. Christmas in July. This is positive 0.14. Now what about copper? Copper, we go here. Copper is plus 2 reducing. Where am I? Copper plus 2 reducing. Positive 0.34. It likes to do that. Christmas. Every time you go to it, you got to touch it. I can do this. There we go. So this is positive 0.34. Add them together, and you get positive 48 volts. What does that tell me?
It's spontaneous.
It's spontaneous. It's positive volts, which means there is man purses being passed around or electrons. Okay, both of them do it okay. Add them together. Think about it. Tin, this is really cool. We're almost done for this period. Okay? This works. Positive volts. There's a reaction here. What are we making? Copper's being produced. Anyone notice a change in color over time? Yeah, it changed color because something was happening. Okay? Now, check it out. Copper plus 2 is pretty good. It's okay, but it does like to gain electrons. It's got an ability to do so. Tin 0, it has some ability to lose them. They're not great individually. But because this pushes a little bit, and this pulls a little more, the pushing and pulling together gives me an overall stronger flow of electrons. Okay, and by the way, if I separate the one who's oxidizing and I'm reducing, that would be the voltage of the battery. How do I make more volts in a battery? Get me something who oxidizes more aggressively, higher what?
Voltage.
Give me something who reduces more aggressively, higher volts here, and I got a greater voltage. Okay? But get back to this. This reaction works. There is what? A pathway for electrons to flow based upon our values of how well they do their individual pushing and pulling. So if I pull this out, we should see some copper. And here is the tin. It's not really, you get that brownish feeling, but that brownish, there's that brown line right there. And that's the copper atoms on top of that. So that, you see the silver up here is the tin, and here is, okay, the copper and some other precipitates in the water. Okay, what happens is copper ions also reacted there, but the point is, you have a reaction. Reaction, no reaction. And hopefully you had some reaction from this demonstration. Okay, so positive volts overall net, negative volts. We can make this happen, need energy. This does it by itself. And because it does it by itself, it's producing energy. It's producing 0.8 volts. And I can take that voltage and ride that energy pony and get free energy from to make electricity or my batteries. Okay? So that's what this means. So measuring voltage of a battery, I'm using the net potentials. When I build a battery, I think about what combination would give me the most. One last point, I will give you a mask break, and I'll go to the bathroom before we do the next thing. Takes the last little piece here, okay? What would be the greatest anode I could use that would oxidize so well, push its electrons onto other things, reducing agent the greatest, that would give me the most voltage?
Lithium.
Lithium.
Isn't that why we use lithium batteries?
Lithium-ion batteries. Now, they're not the same as lithium oxidizing, but it's part of the process. So, the problem with choosing these guys, these metals, to be the anode, they react so aggressively that they corrode in the air. They won't last long. So, as an engineer, when you're thinking about building batteries, you've got to take into account, okay, yeah, these guys are just really, really good at oxidizing, put in my battery, but wait a minute. They react so fast, the battery could explode. Okay, so you have to find a stable way to do that. They use lithium ions, which are actually the stable form. Okay, so these are things to think about. All right, so hopefully that helped your perspective on putting this all together and making our leap into the Daniell cell or a battery. Take a break, please.